The next major topic is something called astronomical gravitation, or sometimes universal gravitation, or sometimes just true gravitation. The key thing here is that although it's called astronomical gravitation, it applies everywhere, even on the Earth. But it's what became apparent as people tried to understand what happened to things in the sky, planets and stars and so on. This is really nothing less portentous than the origin of the scientific revolution. Why do stars and planets move the way that they do? Believe it or not, for most of history, this was a burning question considered of vital importance by philosophers and priests and kings. The motion of heavenly bodies seemed to allow one to predict the future. This is the origin of astrology. And today we laugh, but it's not as crazy as we sound. It's important to remember that you are basically no smarter than ancient peoples, that the human brain has not changed significantly in about 500,000 years. And so they had all the same mental machinery that you do, but somehow they saw something different. It isn't as crazy as it seems, because the motion of the sun and the moon both seem to predict future events fairly well. The sun tells you when to plant or when to harvest, and the moon can tell you when the rains come. And so it's not insane to think that the more subtle motions of the planets might yield more subtle predictive power. And of course, knowing the future is the ultimate kind of power, because if you know the future, you can shape it. So for a long time, these were what we today might consider questions of national security, and people studied the heavens looking for clues and portents. The video to follow here is a time-lapse of the night sky. So somebody took a camera, pointed it at the horizon, left the shutter open, and saw what would happen in very low light over what seems to be about 12 hours. And what you can see, focus on an individual star or pattern of stars, say this triplet. And you see them swirling around the night sky. They're about to go out of frame. Here's a different pattern coming in. So watch that one swirling around. And so we see the stars seem to make patterns, and those patterns seem to wheel around the sky. They seem stable, however. All the stars seem to move together. There's like a star cluster. Putting all those together, which no human eye could see, you would see this. All of the stars, and they all seem to arc out around a central point in the sky. So, the kinematics of stars and planets. If you go out to dark field and lie down, you see the patterns, which we call constellations, that appear to drift across the sky but retain their shape. And if you watch long enough, you see those patterns rise and set, much like the sun and the moon rise and set. Each individual star seems to track out a circle at the same rate, and because of that, the patterns seem to remain intact. They all circle around the same point. This point is called the celestial North Pole. It's directly above the geographic North Pole. And all the stars seem to go around. In fact, this star is the origin of what we call the North Star, or the star Polaris, which just means it goes around the pole. It has a very tiny motion around that point in the sky. Planets also seem to rise and move east to west and set, more or less, but their motion is stranger. Here we'll watch the night sky go by and watch objects on it. But in this case, the sky, quote unquote, is rotating at the same rate as the stars do, and so they don't seem to move. This is what we call motion against the fixed stars. They're not really fixed, but they seem to be, because we're going to cancel out the motion of the Earth, the rotation of the Earth, and we'll see things that move against that background. So anything that is not moving here would, if you were on the Earth, seem to be tracking out about 4 degrees per hour as it swung around the north celestial pole or the south celestial pole. All right, and what we see coming around, so here we have, for instance, Mars. I want you to watch Mars as it goes across. Oops, kind of missed the thing I wanted. Let's see if we can see another one come up. By the way, notice things like Saturn are moving but extraordinarily slow, whereas Mercury is just whipping through the sky field. We should see Mars one more time. There's Saturn moving a little bit too. So here's Mercury. Notice what Mercury just did there, though. Mercury turned around and moved forward. It has a complicated motion. There's the sun going around. All right, it has a very strange and complicated motion, and all of them do. Some of them are too fast to see in this time lapse, but all the planets have these weird little loops and reversals and so on. Notice again that they're not really reversing. They're slowing down relative to the stars. So if you were watching them, they'd always go from east to west on the sky, but sometimes they go as fast as the stars, sometimes they go faster, and sometimes, we'll see, I think here with Mars, let's see. Sometimes they slow down. Mercury just did it there. I guess we're not getting retrograde, but Venus just did it here, where Venus is not really going backward, it's that it's rotating forward at less speed, and so it seems to drift backward. So what's going on? Lots of people had lots of theories. One of the earliest things that are recognizably scientific and non-spiritual comes from a guy named Ptolemy of Alexandria. It was for a very long time, at least in the West, considered to be the explanation, or at least the best explanation. It's a synthesis of about 1,000 years of people's observations and thoughts, but it also has a lot of Ptolemy by himself in it. And he started with what we call a geocentric model. Geocentric because the Earth is at the center. And in these models, the center of the universe. This is the entire observed universe they're talking about, which seems to consist of the Earth and other stuff. In such a model, stars are fixed on a giant sphere, which we call the celestial sphere, which has an axis running through the Earth's north pole and which rotates once per day, carrying the stars along with it. So that grand circular motion is because they're all on one object that is spinning at that rate. The sun, the moon, and planets are each their own spheres, and each sphere has its own speed, which the Greeks would assume were constant because constant speeds would be perfect, and varying speeds are hard to explain. The model cannot actually handle retrograde motion. The idea that, for instance, when Venus or Mercury slowed down and seemed to go back and then seemed to go forward, that backward motion is called retrograde motion. Again, remember, it's not really backward, but it is slower than the celestial sphere, and that changing bit they could not really easily explain. Ptolemy never did. Some of his adherents eventually did compensate later. They added things which are called epicycles and deferents. These are circles that orbit the Earth with the planet orbiting that moving center. That model is a little bit kludgy, but could be made very accurate. The basic idea is that we don't have, for instance, Mercury going around the Earth, which is what the basic model said, but instead there's a point on that orbit, and that point goes around the Earth. But meanwhile, the actual planet, say Mercury, is orbiting that point in a circle at constant speed, but then the center of the circle is orbiting the Earth, and so that lets you get complicated motions for the planet as they orbit the thing that's orbiting the Earth. So this is called an epicycle. Oops. And the offset from the epicycle was called the deferent. And really adding even just one set of epicycles and deferents gets you pretty good stuff. But Ptolemy's data was really, really quite good for the naked eye, and so people would add more as the observations improved, and were able to basically get a pretty decent prediction of when planets would rise and set, which is what we talk about in explaining their motion. They really wanted to be able to predict them so that you could derive things from the pattern. And sort of at the close, well, this is the close of the Roman Republic around 1 AD, it's pretty good, and it's pretty useful, and really for about 1,000 or 1,500 years, it's the standard in at least the West and the Near East. To do it, however, people have to get it better and better. People start adding more and more epicycles and deferents. So instead of saying that, Mercury goes around a point that goes around the Earth, we say that Mercury goes around a point that goes around a point that goes around the Earth, and that there's another epicycle there. And if we need another one, we keep adding it. If you're taking calculus, some of this starts to feel familiar. This is not that different from taking a limiting series. And of course, if you take enough terms in the limiting series, you can get arbitrarily close to the true motion no matter how complicated it is. So it's not a surprise that this seemed to work. But it got increasingly clunky and kludgy. It was harder to do. And as time went on, and observations drifted further from where they were at the sort of outside of the system, it took more and more and more effort to make it work, and it was just wildly inelegant. So around 1500 years after Ptolemy, things changed. They changed in part because of what in the West we call the Dark Ages. In 476, Rome was sacked and the emperor not replaced. The Western Roman Empire fell into chaos and barbarism. There was about 1,000 years, obviously not really unrelentingly dark, but 1,000 years wherein scientific progress was really not carried forward, and in fact even the records of the ancient world were lost. And so people really, they had bits and pieces of this but not much, and they had their minds on other things, so they weren't that worried. But starting around 1400, the Western European economy had recovered enough, and there was the beginning to gel out of the feudal states into the nation states we know today. And there was really, around 1452 is probably a good date. That's when Constantinople fell. So that was the Eastern Roman Empire's capital, often called Byzantium or the Byzantine Empire, although not by them. They considered themselves to be Romans. And in 1452, it fell to the Ottoman Turks. And all of a sudden, it was a good place to no longer be a good place to be sort of a Greek scholar of Greek and Latin Christianity. And some of those scholars fled south, but many of them fled into Europe, where they could find a receptive market for their idea that Christianity was under assault. And they brought with them all the Greek texts that had been lost in Western Europe. So all of a sudden, there's a sudden influx of knowledge about how the world works. People are able to see things like Ptolemy's Almagest in its original form, and they're able to notice that it doesn't really work that well. It's kludgy. People had thought of it as this perfect thing that they only had imperfect copies of. Now they have perfect copies, or nearly perfect copies, and it's still wildly imperfect. There's also been 1,000 years of drift in astronomical data. In other words, the data does change because the model is not 100% perfect, and so it's become wildly out of sync, and it requires a lot of work to get back into sync. And meanwhile, there's been a philosophical shift, and it cannot be stressed enough that this is a philosophical shift, which is that in the late Middle Ages philosophy of this time, the conception of the role of the planets and such had changed. Philosophically, the sun was the visible representation of God. These were still Christians. They weren't sun worshippers, but the sun was considered to be a manifestation of God's love for the world. It brings light and heat. God is all high in this model, and therefore the sun should have the position of prominence, which is the center. So it sort of offended late medieval philosophers that we would put dirty and corrupt earth at the center of everything. This should be the perfect sun that is at the center. That gets Galileo into trouble a little bit later, actually. We'll talk about that. In this new or heliocentric model, in the heliocentric model, the sun is at the center because Helios is the sun. And the earth and other planets move in circles around the sun. Then the moon moves in a circle around the earth. And the stars are themselves each distant objects at varying distances. That's optional, but most people seem to think that. Movements of the stars then is explained simply as the rotation of the Earth. The reason that they seem to rotate around a line that connects the celestial sphere to the North Pole of the Earth is they're actually just the Earth is rotating around its North Pole. And we're seeing distant objects that are still moving around because they seem to be. It does have failures. It cannot explain what's called parallax. We'll talk about that on the next slide. If the stars are really distant objects and the Earth is moving around the sun and we're viewing them, why don't they seem to change during the year? And that's a big issue. It's not a new issue. The Greeks also knew about it. The Greek solution was that the stars rotated and we don't. That the reason we don't see them moving in different places is we're at the center. And Copernicus and his ilk are saying, no, we're not the center. So that old problem rears its ugly head again. And then explains retrograde motion really simply, because now the reason that, for instance, Mercury seems to move backward against the stars is just because sometimes the Earth is catching up to it in the orbits, and sometimes it's moving past it. It's on the other side, going the other way. So it's really easy. But it does not match the actual observed retrograde motion. It's important to put that here too. The Copernican model is not better at explaining the data than Ptolemy. It's not a better match. In fact, it's a worse match. In almost all ways, the Ptolemaic model is better at predicting the rising and setting of planets and where they are in the sky. So that kind of contradicts the middle school version of this, where it was like, oh, people got better data and discarded the old model and went to the new model because it was a better and more accurate explanation. Turns out that's not really true. All right, they moved because those who did moved because philosophically they no longer liked the underpinnings, the metaphysical underpinnings of the Ptolemaic model, and they wanted a more congruent Christian model. Actually, not even that, but a late Augustinian Christian model. By the way, how did Copernicus get rid of the problem that retrograde motions worked but not entirely perfectly? Yeah, he brought back epicycles and deference. So the things that made the Ptolemaic model clunky and kind of unappealing end up going into the Copernican model as well, because that's the only way they know to take care of these deviations. Copernicus gets a lot of credit in the history of science. I think too much, to be honest. So what is this thing called parallax that ends up confounding the Copernican model that needs to be explained? Here's a brief explanation.
Have you ever traveled down a road in a car and looked at the mountains or hills in the distance? If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower, and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seem to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the Sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice.
It's important to understand here something which she does not mention, which is that to the naked eye, you don't see the stars move at all. So it is true that nearer stars seem to move, but you do need telescopes to see it, which is one reason why the ancient peoples didn't worry too much about it.
Now, if we measure how much a star moves when the Earth does one complete trip around the Sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the Sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the Sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
As a very quick aside, the nearest star is about 4 light years from the Earth. That's something like 276,000 astronomical units, or 276,000 times the distance of the Earth to the Sun, which means the angle that comes out would be something like 6.3 times 10 to the minus 8 degrees, or something like 60 billionths of a degree, which you can't resolve with the naked eye. So people didn't see parallax until telescopes were invented. All right. So the status here at the end of sort of the 1400s is a bit of a mess, the early 1500s, because you have the Ptolemaic model, which is old and creaky but reliable, and the new Copernican model, which is shiny but also kind of creaky and unreliable, and no one really knows what to do or where to go forth. There's a lot of Sturm and Drang over this. There's a lot of angst. Copernicus publishes his book on his deathbed because he doesn't want to be burned at the stake for being a heliocentric the way, say, Giordano Bruno had been a few years earlier. It's a bit of a mess. And into that mess comes the person who I think is the hero of the scientific revolution. That person is Johannes Kepler. Kepler works with a guy named Tycho Brahe, who's the last of the great naked eye astronomers. Tycho is fantastically good, builds these things that help him measure things, but he's before the telescope. He's the last great astronomer before the telescope. I have to say it's union regulations that cannot mention Tycho Brahe without telling you the one thing everybody remembers. Tycho had a nose made entirely of silver. He had gotten involved with a duel when he was young with another person over, believe it or not, astronomy. That person cut off the tip of his nose, and Tycho decided to get a silver tip fashioned. So for the rest of his life, he wore a silver tip on his nose. It has nothing to do with his astronomy, but gives you some idea that this was the age of badass astronomers and scientists. Tycho spends decades, he compiles decades of very detailed and very accurate tables of the positions of all the known planets, that is, Mercury, Venus, Mars, Jupiter, and Saturn. At this time, that's what planet meant. Planetos actually is the Greek word for wanderer, and these were the objects that wandered against the sky, that didn't move as fast as the stars. The other two planets there being the sun and the moon, which we no longer consider planets, but the ancient peoples did, because they also wandered against the star field. Tycho is not so great at math, so he hires Kepler. Tycho has his own bizarre mix of geocentric and heliocentric. It's a very strange theory. He wants support for it. He hires Kepler. Kepler doesn't give him support for it. Kepler ends up saying, your model's crazy. And they have a bit of a falling out and then a reconciliation. Eventually, Kepler gets Tycho's notebooks, and he begins crunching the data that Tycho got. He does it for about a data, and he tries to fit that into his own heliocentric model. Kepler's heliocentric model is also very strange. He says there are 5 planets, so if you include the sun, there are 6 gaps that you have to explain, and there are, there are 5 gaps you have to explain, and there are 5 so-called Platonic solids, things that have that are regular polyhedrons. So a regular polygon is a thing that has all the same sides and all the same angles. A Platonic solid is a regular polyhedron, so it's a thing that like a 4-sided pyramid, where it would have the same face repeated at the same angles. Or maybe a better example is, of course, the standard die, just a cube, where all the faces are the same and all the angles are the same. And it had been known since ancient times that there were exactly 5 of these, not the infinite many that you might expect from polygons, where there are infinitely many polygons, but the need to curve them over themselves in 3-dimensional space means that there are only 5 of them. They have 4 or 6 or 8 or 10 or 12 or 20 sides, and that's it. Fans of Dungeons & Dragons, by the way, recognize these as most of the dice that you roll. That's an aside that had nothing to do with Ptolemy, of course, or Plato. But Kepler's like, well, 5 Platonic solids, we need to explain 5 planetary orbits, and he really wanted to make this the case, that you had these sort of nested Platonic solids inside the spheres that carry the planets. He worked for about a decade. He didn't get anywhere. It turns out this theory is not, in fact, at all true. And so he does not succeed in making Tycho's beautiful data fit his beautiful model. But that failure turns out to be a success in disguise. Having convinced himself that Tycho's data cannot fit the circles he would needed for his usual Copernican model, or even for his crazy little model, he comes to a bold conclusion that underlies all of modern science, and he might be the very first person to state explicitly. If the data and theory conflict, then the theory must be abandoned. In other words, and cannot state this enough, the universe cannot be wrong. You cannot say things should be different because they look nicer or they make more sense. In the end, you have to explain the data in front of you. And this really is the start of the scientific revolution. And while he probably isn't the first person to say it, he says it successfully and forcefully and loudly, and is able to do stuff with it that we'll talk about next time. But the philosophical bit should not be undersold. He launches the scientific revolution by saying, I don't care if your model is pretty, the data wins.